Hey everyone, and welcome! Today, we're going to pull back the curtain on something pretty fundamental to how computers work. How your machine takes a simple file full of code and, well, breathes life into it, turning it into a program that actually runs. Let's get right into it.
Have you ever really stopped to think about it? You find an icon, you double-click it, and boom! This complex application just springs into existence on your screen. It kind of feels like magic, right? Well, today, we're going to break down that magic piece by piece.
So, first things first, we need to figure out where a program actually lives and does its thing. See, when it's not running, it's just a file, sitting quietly on your hard drive. But the moment you launch it, it needs a new home, a place to work.
And that new home is your computer's RAM, or random access memory. A really good way to think about this is that your hard drive is like a giant library where all the books are stored for the long term. RAM, on the other hand, is like the desk where you open up a specific book to actually read it. It's way faster to get to, which is exactly what a running program needs.
And, just like every single house on a long street has its own unique address, every single little spot in RAM has a memory address. This is how the computer knows precisely where to find any piece of information it's looking for, whether that's a line of your code, a variable, or, a picture of your cat.
Now, behind the curtain, this is way more complicated than it sounds. A simple address is actually a secret code that tells the hardware exactly which memory chip, which row, and which column to look in. But here's the good news. Your operating system is like a fantastic manager. It handles all that nitty-gritty complexity for you, giving your program a nice, simple, organized view of its world.
Okay, so our program has found its new home in RAM. But what does it actually look like now that it's alive? How is it all structured in there? Let's take a look. I absolutely love this analogy. Think of your program's code as like the blueprint for a video game character. It's just a static design. The process, though, is that character actually in the game, running around, jumping, making decisions, and reacting to everything. It's the living, breathing, dynamic version of that static code.
And that gets us to the more official definition. A process is an instance of a program in execution. It's following its instructions one after the other, and with every single step, its internal state, things like the values of its variables, can change. Just like our game character's health or score might change as they play the game.
So here's a look at how that character's world is laid out in memory. Right at the bottom, you've got the code, the actual instructions. Just above that is the data section for variables that don't change size. Then you've got these two special areas that can grow. The heap, which grows upward for memory you create as you go, and the stack, which grows downward to keep track of function calls. They grow towards each other, which is just a super clever way to make sure no space is wasted.
Okay, so right now, your computer is probably running dozens, maybe even hundreds of these processes all at once. You've got your web browser, your music player, all sorts of background tasks. So how on earth does the operating system keep all of them straight?
Well, it gives each and every one a unique process ID, or PID for short. It's literally like an ID card. Whenever the operating system needs to do something to a specific process, like give it more memory or tell it to close, it uses that PID to make sure it's talking to the right one.
And this is a perfect example of why every process is unique. Let's say you open two different web browser windows. They're running the exact same program, but they become two totally different processes. Why? Because their experiences are different. You click on different links, the time is a few milliseconds apart, the network data they receive is different. All these unique inputs cause their code to take different paths.
But what happens when a process ends? Can the OS immediately give its PID, say PID 123, to a brand new process? Well, it could, but that's actually pretty risky. The new process might accidentally stumble on some leftover data or resources from the old one, and they could cause all sorts of bizarre bugs. The much safer and smarter approach is to wait a little while before reusing that ID.
Now, this is where things get really cool with modern technology like containers. Containers use a clever concept called namespaces. The best way to think of it is like having separate apartment buildings. Each building can have its own apartment 101, and there's no confusion, right? Because they're in different buildings. This is how two completely separate containers can both have a process with the exact same PID, like PID1, and everything just works.
All right, so we've established that a process runs its instructions one by one, but how does the CPU know which instruction is next in that long list of code? It needs some kind of guide, a sort of internal GPS.
And that GPS is called the program counter, or PC. It's this tiny but unbelievably important part of the CPU. It's a special little pointer whose only job is to always hold the memory address of the very next instruction the CPU is supposed to run. It's the ultimate what's next list.
And its job is just a simple, relentless loop. The CPU looks at the program counter to see where to go. It fetches and runs whatever instruction is there. As soon as it's done, the program counter automatically moves to point to the next instruction in line. And this cycle just repeats, billions and billions of times every single second.
Okay, so here's a super important design choice. Where should this program counter be stored? If you put it out in the main RAM, the CPU would have to make that relatively slow trip to memory for every single instruction just to figure out what to do next. That would be an absolute disaster for performance. So the smart solution, the way it's actually done, is to keep the program counter in a CPU register. That's a tiny piece of super fast memory right inside the CPU itself, which makes the whole process blazing fast.
But hold on a second. If the CPU can only do one thing at a time, how can you run your browser and listen to music and have a game open all at once? The answer is, you can't. It's all an illusion. Your computer is just really good at switching between all those tasks incredibly fast. This super fast switching is called context switching, and honestly, the best way to think about it is like saving your progress in a video game. When it's another process's turn to use the CPU, the operating system basically hits pause on the current one. It carefully saves everything about its current state, especially that super important program counter, so that when its turn comes back around, it can pick up from that exact spot without skipping a beat.
So where does the operating system store all this saved game information? Well, for every single process, it keeps a master record, a kind of ultimate character sheet.
This master record is called the Process Control Block, or PCB, and it holds absolutely everything the OS needs to know. Its unique PID, the saved program counter, the state of all the CPU registers, which files it has open, the whole shebang. It's the complete profile for that process, ready to be loaded back up the next time it gets a turn to run.
All right, so let's do a quick recap. A static program on your drive becomes a living, breathing process inside your computer's RAM. Every process gets a unique ID and has a specific layout in memory. The program counter acts as its GPS, guiding the CPU from one instruction to the next. And to juggle all these tasks, the OS is constantly saving the game with context switches, storing everything in that master file called the Process Control Block.
And that brings us to our final big question. We know the OS can switch between all these processes, but with so many of them demanding attention, how does it decide which one gets to run next and for how long? Well, my friends, that is the art and science of process scheduling, and it's a topic for our next explainer. Thanks so much for joining me.